Okay, hello everyone in a new video. So we have reached part 11 of chapter 8, which is the chapter of Newton's second law for rotation for grade 11 students. And by this we have completed the explanation of this chapter. And in this one I'm going to give some notes that are important for the rest of the exercises regarding this chapter. And as always, whenever needed, we can refer to this table. Let me start by the following note. So we have discussed these notes, or I've mentioned them. I have mentioned during the previous parts that I will discuss these notes. So let me start by the following example. So here suppose we have the solid S, the solid M, and this is a support, and they are connected by two strings that are inextensible. This is the point A, point B, the points of contact respectively. We have the tension here T1, and here we have another tension. So notice that in this case I have represented these tensions having the same length just to indicate that they have the same magnitude. So in this case we have that T1 is equal to T1 prime, and the reason is given by an extensible string. Now, because the string is extensible, so the tension is being transmitted equally on both sides, and more importantly because it doesn't overpass another body that is allowed to rotate. Now I will explain more what is meant by that, but for this one here, because the tension, the string is inextensible, the tensions T1 and T1 prime are equal. Now, in order to explain the second note, let me consider the following document. So here in this one, we have several tensions. Let me label them. Now we are in note number 2. Let me say that this is the tension T1, and this is the tension T1 prime. And this is the tension T2, and this is the tension T2 prime. And let me say that T1 is equal to T1 prime, and the reason is given by an extensible string. So because T1 and T2 are tensions along this inextensible string, and an extensible string transmit tension equally at both ends, so T1 is equal to T1 prime, and in this case T2 is also equal to T2 prime, and the reason is given by an extensible string. But now we cannot say that T1 prime is equal to T2 prime, simply because although the string is inextensible, but it overpasses a body that undergoes a rotation. So here let me repeat that T1 is equal to T1 prime because simply the string is inextensible and it doesn't pass through another body that undergoes rotation. T2 is equal to T2 prime because the string is inextensible and it doesn't overpass a body that undergoes rotation. Now in this case, T2 prime is not equal to T1 prime because although the string is inextensible, but it overpass a body that undergoes rotation. And they might be equal if the following is true: if the string is inextensible and the pulley is of negligible mass. So this is the pulley. And let me explain the reasoning behind this. So why T1 prime and T2 prime, they are equal in this case, and they are not equal in general. Let me explain. So now we can consider the sum of moments around an axis delta, which is this one, passing through the pulley. Let me sketch it here in a more clear diagram. So this is the pulley, and this is the tension, say for example T1 prime, and this is the tension T2, like this. So we can discuss Newton's second law for rotation, and we say that sum of moments around the axis delta is equal to I alpha. Here for sure we have the weight which is vertical downward like this, and we have the normal reaction, or the reaction, which is like this. So this is the weight and this is the reaction R, and the sum of moments in this case around delta is equal to I alpha. Now here we have the moment of the tension T1 prime around delta plus the moment of the tension T2 prime around delta plus the moment of R around delta plus the moment of W around the delta is equal to I alpha. Now here I'm not considering that the pulley is at equilibrium, we don't know. And let me consider this is the positive direction of rotation. Now directly we can say that the moment of R is 0 and the moment of W is 0, because both weight and R, their line of action passes through the axis of rotation. Now we are left with the moment of the tension T1 prime around delta plus the moment of the tension T2 prime around delta is equal to I alpha. Now the moment of the tension T1 prime around delta is equal to T1 prime tangential multiplied by the distance d, which is the radius. Now one can try by geometrical inspection that the tension is always tangent to the circle. So T1 prime tangential will either be plus or minus sign, so it is, in this case it will try to rotate the disk in the positive direction, times T1 prime, and here no need for the cosine because the tension will always be tangent to the circle. Okay, and one can inspect this fact by geometrical construction, that the tension along the string is always tangent to the pulley. Now so in this case the moment of the tension T1 prime around delta is equal to T1 prime multiplied by the distance d, which is R. And similarly the tension, the moment of the tension T2 prime around the axis delta will be a minus sign because it will try to rotate like this times the distance, which is R. So here we have T1 prime multiplied by the distance R minus T2 prime multiplied by the distance R is equal to I alpha. Now if the pulley is of negligible mass, then in this case I is equal to 0. Why the moment of inertia in this case will be equal to 0? Because we know that the moment of inertia, if we refer to this table, the moment of inertia in all of the cases is proportional to the mass. In every case that we may consider or think about, the moment of inertia is always proportional to the mass. So if the object that you are considering is of negligible mass, then the moment of inertia is equal to 0. And this gives us this T1 prime multiplied by R minus T2 prime multiplied by R is equal to 0 multiplied by alpha, which is 0. And we can simplify by R, which means that T1 prime is equal to T2 prime. For this reason, whenever the pulley or the object is of negligible mass, in which this object connects, or the string overpasses this object, so the tension will be equal in this case. Otherwise, we cannot say that T1 prime and T2 prime are equal. So here we require an important condition, which is that the string is inextensible and the pulley is of negligible mass, and this only happens, or we require this condition, when the string overpasses a certain body undergoing rotation. Now here, for example, one can say that, okay, this can also be equal to 0 if alpha is 0, which is in the case of UCM and equilibrium. So it is true, but we will not consider these two cases. We'll consider the general case in which whenever the pulley is of negligible mass, then I is equal to 0, which means that T1 prime is equal to T2 prime, and this can be mentioned always like this. Just we add the following statement: the pulley is of negligible mass. Okay, so usually this statement we give it half a mark whenever we need, or we are asked to equate this tension to this tension. Now so this is the second note that I wanted to discuss. The third note that I wanted also to discuss, the tension causing moment. So here I'm talking about the moment of a force and in specific the tension, moment of a tension around a pulley. So by the pulley, remember that I mean a disc, is always in the tangential direction. And this note I have used above. Okay, so always the tension causing moment around the pulley is always in the tangential direction. So no need to project, we will simply place either a plus sign or a minus sign. And I repeat, I will not discuss why this is true, but it can always be inspected by geometrical construction. Okay, so whenever we are talking about the moment produced around the tension, we will not project. Okay, so the value of cosine will be always 0. Now the fourth note that I wanted to discuss, which is also extremely important, which is the free fall. Now let me consider here what is meant. Let me see what is meant by the free fall. Now suppose here we have a solid S free falling under the action of the weight, and we are interested in applying sum of forces is equal to ma. So, or let me say we are interested in determining the acceleration. So we apply Newton's second law, which is given by sum of forces is equal to ma, and neglecting a resistance, we have the weight is equal to ma because there is no other force acting other than the weight. And if you consider the positive y direction, okay, it is independent whether it's up or down because we will determine later the magnitude. Let me consider that this is the positive direction of the y-axis, and we will project along the y-axis. So here simply we drop down the vectors, we have wy is equal to may, which means that, and now wy, it is in the positive direction of the y-axis, so it's plus w, no need for any cosine because it's parallel may. We know that the value of the weight is given by mg, which is equal to may, and in this case m cancels with m, so g is equal to ay. So the value of the acceleration is simply the gravitational field strength, and if we want to determine the total acceleration, because this is a component and the acceleration vector is given by axi plus ayj, so simply a will be given by the square root of ax square plus ay square. This is 0 because no acceleration along the x-axis. All of the motion occurs along the y-axis, and in this case, so if you plug down here, it will be given by g. So the value of the acceleration is given by g, which is equal to 9.8 or 10 meters per second square. Now I wanted to compare this case with the following case. And here I wanted to mention the following important remark, that the acceleration is independent of mass. So any free falling body will be accelerating under acceleration given by 10 meters per second squared. So each second the speed will increase by 10 meters per second. Okay, now what about if the solid is falling along an inclined plane? And the angle of inclination is given by alpha. Here we have a solid. So we are interested in determining the value of the acceleration, which is given by A. So in order to do so, we need to represent the forces acting on the solid S. We have the weight, which is vertically downward, and we have the normal, which is normal to the plane like this. Then we will choose the positive x direction to be like this in the direction of motion, and the positive y direction is perpendicular to the x direction, which is like this. And here in this case we are neglecting friction because I want to compare it with the free fall, and in the free fall we have neglected the air resistance. Okay, so in this case we will also apply sum of forces is equal to what? MA, and we have the weight plus the normal is equal to MA. Now let's determine the projection of each force. So Wx, Wy, here we have Nx is equal to 0 and Ny will be simply plus N because no projections. As for Wx, now it's pointing in the positive direction of the x-axis is plus, so this will be pi by 2 minus alpha, and this is pi by 2, so it will be plus w multiplied by cosine of pi by 2 minus alpha, and this is minus w, so this angle will be here alpha, it will be cosine alpha. So now referring to this equation, and let me say projection along the x-axis, so here we have Wx plus Nx is equal to Max. So Wx is given by W sine alpha, because cosine pi by 2 minus alpha it will be sine alpha, plus 0, which is equal to Max. So in this case mg sine alpha is equal to Max, and here m cancels out with m, and Ax it will be given by sine alpha, so g sine alpha. And if you want to determine the total acceleration, the acceleration will be given by the square root of Ax squared plus Ay squared, and in this case Ay is 0 because no motion along the y-axis, and this is given by g sine alpha. And here let's recall that sine alpha is a value which is between 0 and 1. So if you consider that we are working in the first quadrant, no need to say that it's between minus 1 and 1, let's say between 0 and 1. So now we come up with the following conclusion. So let me say that sine alpha is less than 1. Okay. So whenever we are multiplying something with sine alpha, the number will decrease. And recall here that alpha is the angle of inclination. Okay. So what I'm trying to say is that if we are in the case of the free fall, the acceleration is given by g, and in the case of we are and in the case of inclined plane, let me say by alpha, where alpha is the angle of inclination, then the acceleration will be proportional to g, but the proportionality constant is given by sine alpha. So always whenever the body is undergoing a free fall, the value of the acceleration will be given by 9.8, which is 10 meters per second square. In the case of an inclined plane, the value of acceleration will be given by 10 meters per second square, but is multiplied here by a value which is sine alpha, which is less than 1. So the value of the acceleration will decrease depending on the value of the angle, so it will be 10 multiplied by sine alpha. Okay. Now, these are the following notes that I wanted to consider before we start solving the exercises. Now, in the following exercise also I will consider another note, but I will discuss this note during this exercise. Okay. Now, exercise number 18, they are telling me two particles S1 and S2 of respective masses M1 and M2 are placed on two frictionless inclined surfaces of respective inclinations alpha and beta. We have the values of sine alpha and sine beta. S1 and S2 are joined by light and extensible string that passes over a light pulley. So here, because we have an inextensible string and the pulley is light, so the four tensions that we have here, 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 and here, all of them are equal. Okay, but more than that, whenever we are calculating, we need to justify properly whenever. So if we want to justify that this tension is equal to this tension, we need to say that the string is inextensible. Whenever we are justifying that this tension is equal to this tension, we need to say that the string is inextensible. Whenever we are justifying that this tension is equal to this tension, we need to say that the string is inextensible. Moreover, that the pulley is of negligible mass, which is a light pulley. Okay. Now notice that, let me say here that we have the solid S1. The mass of S1 is given by 3 kilograms. And we have that sine alpha, which is the angle of inclination with respect to M1, is given by 0.3. We have the solid S2 of mass M2 is equal to 2 kilograms, and the value of sine beta is equal to 0.5. And for sure we have that the value of G is given by 10 meters per second square. Okay. Now before I start reading the problem, let me say the following. S1 is falling on an inclined plane, so its acceleration will be given by a g sine, so g suppressed by the value of sine alpha, in which alpha represents the angle of inclination with the horizontal with respect to S1. As for S2, this is A1. As for S2, it will undergo an acceleration given by g sine beta, in which beta is the angle of inclination with respect to S2 and the horizontal. Okay. Now in number 1, they are telling us indicate the sense of motion of S1 and S2, and this is the first time that we face problem of such type. Now let me calculate the acceleration of A1, or before calculating the acceleration of A1. So now they are telling me indicate the sense of motion of S1 and S2. Okay. In order to justify this problem, let me consider the following case. Now suppose here we have a pulley, and here we have a solid S1, and we have a solid S2, and we are asked the following question: indicate with a justification in which direction the pulley will rotate. So we know that this answer can be justified by comparing the weights of S1 and S2. So we determine the weight W1, and we determine the weight W2, and we compare W1 with W2. If W1 is greater than W2, so the action of this solid will be greater than this solid, so the pulley will rotate like this in the anti-clockwise direction. Now in the case of W2 will be greater than W1, then the pulley will rotate like this in the clockwise direction, and this is reasonable because this weight will cause a tension like this, comparing it with this tension will be greater, and etc. Okay, so the direction of rotation of the pulley or the direction of motion is determined by the strength of W's compared to each other, whether W1 is greater than W2 or vice versa. Now here it's exactly the same, but we will not compare W, we will compare W sine alpha. Because notice that W previously was given by M multiplied by G. Here, because we have an inclination, we will not compare W, we will compare the new W, which is given by mg sine alpha. Okay, we cannot compare the acceleration, we need to compare the forces. So here in this case, I know that this is the first time we face such a problem, but from now on we have learned this trick. So in this case we will determine m 1 g sine alpha, and in this case we will determine m2 g sine alpha, sorry, g sine beta, and the one with the greater value will so if for example this is greater than this, then the motion will be in the direction of S1 and not in S2. Okay, so here this part represents the acceleration of A1 and this part represents the acceleration of A2, but it is not enough to compare the accelerations because the acceleration doesn't reflect the strength of the force. We need to calculate the magnitude. Okay, so I repeat, here we are interested in indicating the sense of motion of S1 and S2, which is related to the weights of S1 and S2, but we will not calculate the weight which is given by mg. We will calculate the weight suppressed by the factor of sine alpha and beta, because the weight is suppressed by the following factor. So let me determine first m1g sine alpha, which is given by 3 multiplied by 10 multiplied by 0.3. Now plugging this on the calculator, this is given by 0.9. This represents, so sine alpha doesn't have any unit, this represents the magnitude of a force, then this is given by newtons. Now as for m2 g sine beta, this is equal to 2 multiplied by 10 multiplied by 0.5. So this will be, let me check on the calculator. I think this is wrong. This is 9 newtons and this is 10 newtons. So let me say since m2 g sine beta is greater than m1 g sine beta, then the direction of motion will be along S2. And here by along S2, I means as if S2 is falling down. Okay, as if S2 is falling along the inclined plane. Now in number 2 they are telling me determine the acceleration a1 of S1 as function of m1 g sine alpha and t1, the magnitude of the tension force in the string at the point of contact with S1. So here they are asking me to determine the acceleration, and this can be determined by Newton's second law for translation. Because S1 undergoes a translational motion, it doesn't rotate, and moreover they told me the acceleration. If they are asking about the angular acceleration, they would have more specific. And the tension T1 is the magnitude of the tension for in the string of the point of contact with S1, so this is the tension T1. Okay. Now let me here represent another diagram which is more clear. So let me consider that this is the positive direction. Okay, so because S2 is moving downward, now, okay, first of all, we need to fix the direction of motion of the system. And because we have said that S2 will go downward, so it will be moving like this. So this is the positive direction of motion. And now let me represent the forces. Here we have the weight, and here we have the normal. Now so this is W1. Let's determine the projection of each of the forces. Here we have W1x, so it's pointing in the negative direction of the x-axis. So this angle here will be pi by 2 minus alpha. This is parallel to this, so this is also pi by 2 minus alpha. So it's given by minus w cosine of pi by 2 minus alpha, which is minus w sine alpha. As for w1y, so here this angle will be simply given by alpha. So, and it's pointing in a negative direction, so it's minus w cosine alpha. As for n1x, so let me say this is n1 because here we have another normal which is n2. It will be 0. As for n1y, it will be plus n1. And now let's apply Newton's second law. Apply Newton's second law. Which is given by sum of forces is equal to ma. And the different forces acting on the solid S1, here we have the tension T1 also. Now T1x is equal to 0, and T1x, T1 it's pointing in the positive direction, so it's plus T1, and T1y eventually will be 0. Now let me replace in this equation the different forces that are acting on the solid 1. We have T1 plus W1 plus N1, this is equal to ma. And we are interested in determining the acceleration. In order to do so, this is a vectorial equation. We don't know how to deal with vectorial equations. We need to project along the x-axis and along the y-axis. Then let me project along the x-axis. Now simply we drop down the vector quantities, and each vector quantity will carry the label x.